So today we're going to multiply matrices and we're going to actually start to use matrices. So we'll figure out why we're doing all of this. But first let's remember how to multiply matrices. A 2 by 2 times a 2 by 2, I can multiply those together. I'm multiplying the 4 times -3, which is -12, and then adding that to the -1 plus 1, so that's going to be -13. And you just got to kind of keep your work straight. It's so nice when there's a 0. 7 times -3 is -21. And then since 1 times 0 is 0, I'm good there. Now I have the 4, -1 times the 2, 5. So I've got 8 plus -5 would be 3. So 3. And then finally I have the 7, 0 times the 2, 5 would be 14 plus 0, or just 14. Remember, how to find the inverse of a matrix is that you do 1 over the AD minus the BC. So this is -6 minus 40, or -46. Does not get distributed. Switch spots, switch signs. So we'll switch spots here with the 6 and the -1, and switch signs with the -8, -5. And we didn't really understand why we were doing that, right? We just were like following the rule. And now here we're going to see why we're doing it. So the reason is we can actually use inverse matrices and matrix multiplication to solve a 2 by 2 system. And you might say, we already know how to solve a 2 by 2 system, which we do. But here's another way. So I'm going to do number 4 first. Number 3 actually is one of those that turns out to be empty set. I can go back and do it later, but I don't want to start with one that's empty set. So here's how we would do like a normal one. So we're going to rewrite the problem as a matrix problem. 1, -1, 2, 3. And then if we multiplied that by the column matrix xy, we would get the column matrix 2, 8. This is just basically representing the problem in a different way, right? So now what I'm going to do is multiply both sides by the inverse of the matrix. Just like we would solve any question in algebra by multiplying both sides by the inverse or adding the inverse, same thing. So if I take this matrix here and find the inverse, it's going to be 1 over 3 minus -2, so 1/5, and then switch spots, switch signs, so 3 and 1 switch spots, and then 1 and -2. And the golden rule, you'll remember, of algebra is always do unto one side as you do to the other. So I'm going to multiply both sides by that inverse. I like using different colors to represent the inverse because it's like so much writing, right? 2 and 8. So now I've got all of this writing. Oops, all of this. But if I remember, what happens when you multiply an inverse of a matrix times a matrix? Do you remember? You could do this out by hand. Like you could be like, oh, okay, 1, 2, 3, 1, 3 plus 2 is 5. Maybe we'll do that for the first time. So 1/5 and then 5. And then here, if I multiply here, 1, it's a -1 rather, -1, 3, 3, 1. So it's going to be 3 minus 3 or 0. Similarly, when I come here, I get -2 plus 2 is 0. And then here I get 2 plus 3, which is 5. Equals. And then here I might as well multiply these two together. So it would be 2 times 3 is 6, plus 8 is 14. And then it looks like -2 plus 8 is 4. If I were to distribute my 1/5 now, do you agree that I would get the 1, 0, 0, 1 identity matrix times xy? And when I multiply by the identity matrix, again, you could do this if you wanted to, but you're going to see that it's just going to equal xy. And I can distribute that 1/5 now at the end, 14/5, 4/5. So that gives me my ordered pair, 14/5, 4/5. It's a lot of writing, but really all I'm doing is rewriting it as a matrix at this step, multiplying both sides by the inverse. Eventually, we're not even going to show the work here. We're just going to recognize that multiplying by the inverse times a matrix is really the identity matrix, and multiplying by the identity matrix keeps something exact same. And here we get our answers. It's interesting that our answers were actually kind of tougher answers, fractions, 4/5 and 14/5, but it was kind of effortless, really, to get those fraction answers. Because I'm out of room here, I'm just going to erase this, what I just did, and then use that space to do number 5. And then after that, we'll be in good shape. So let's see, number 5. First, I'm going to rewrite this as a matrix. So 3, -5, 4, 3 times xy, I'm just getting that from the coefficients, equals -13, 2. I'm going to multiply both sides by the inverse. Inverse is 1 over the determinant. So I have 9 minus -20 is 1 over 29. Switch spots, switch signs. So 3, 3, switch spots, and then 5, -4 when I switch signs. That's going to be on both sides of the equation. 29, 3, -4, 5, and 3. I'm going to rewrite everything else kind of as it was. 3, -5, 4, 3, and xy. And we realize this is a lot of writing, right? And then this is the -13 and the 2. Now here's the fun part. On this left-hand side, this entire thing, and you could test it if you wanted to by multiplying it, or you can just be like, this is what she told us, it always is going to reduce to the identity matrix. And that's by design, right? We multiplied by the inverse. And when we multiply by the identity matrix, we just get xy. On this side, first maybe I'll multiply that in. So what do I have? -39, this is 1 over 29, right? -39 plus 10 is -29. And then here, 13 times 4, what's that? Oh yeah, 52. 52, I'm multiplying here and here. 52 plus 6, isn't that 58? And if I distribute my 1/29th, I get -1, 2. So my ordered pair that solves the system is -1, 2. Now if I go back to this first one that I skipped, I'll rewrite it now as a matrix equation. And I've already told you that the answer is empty set. xy equals 5 and 1. If I go to multiply both sides by the inverse, 1 over AD minus BC, so I have 1 over, it's -4 minus -4, or 1 over 0. And once I see that, that means that there's no inverse, which means that the problem just like kind of falls apart after that, and there's basically no solution. Of course, on a quiz or a test, I would always give you one like 4 or 5 that has a solution. That's the main thing that we're doing today. This last piece is the 3 by 3 determinant. This is actually setting us up for tomorrow's notes, but we will go through it anyway. You see this crazy formula, right? This is a formula for the determinant of a 3 by 3 matrix, and it's a lot easier than it looks. So you see how the matrix is labeled A1, A2, A3, B1, 2, 3, C1, 2, 3, right? So you can just kind of plug in what you see. So A1 here would be the 1. So it's going to be 1, right? 1 times, why isn't it letting me write? Try it with my finger. 1 times B2, C2, B3, C3. So in ours here, it's going to be the 5, 6, 8, 9. Try another color. 5, 6, 8, 9. It doesn't want me to write it. I'm going to try it with my finger. 5, 6, 8, 9. 9. Then I see a minus sign. And then it says A2, so in ours that's a 4. B1, C1, B3, C3, so 2, 3, 8, 9. Then I see a plus. A3 here is a 7. B1, C1. So then this is going to be, what, 2, 3, 8, or 2, 3, B2, C2, 5, 6. Right? So I basically just went through and plugged in what they told me. Now for each of these, the bars here mean the 2 by 2 determinant. So this is going to be 1 times the 2 by 2 determinant. 9 times 5 is 45 minus 48. Or 1 times -3 or -3. Here I have -4. 5 or 2 times 9, that's a 9, is 18 minus 24. So -4 times -6 is going to be positive 24. And then here I have 7 times 12 minus 15, or 7 times -3, or -21. And the final answer adds those up, in this case 0. You might say, how did she do that? I really just plugged into the formula. And like other formulas, kind of reminds me of law of cosines, where we're just going to see the pattern eventually. I got to erase this, sorry, to give more room to do the second one. Let's see if my pen will work here. Let's try this again. So again, just following in the formula, -1 times B2C2 B3C3. So that's going to be 6, -1, -3, 0. And then I'm going to subtract A2, which is 5. B1C1. So the one way I remember it is like when you have the 5, it's almost like you're eliminating the row and the column that the 5 is in. And then the numbers you're left with are the ones that go in the determinant. And then for the next one here, the last one, plus A3, A3 is the 2. So if I eliminate the row and the column that the 2 are in, then I see the -2, -3, 6, -1. So now for each of these, I'm going to actually do the determinant. -1, come on, -1, and then this is going to be 0 minus 3, which is -3. I'm just doing the determinant. -5, 0 minus -9 is 9. And then here, -2 minus -18, -20. So I have 3 minus 45 minus 40, or -85 plus 3, which is -82. Might as well do the last one. So sorry, I got to delete again here. So might as well do the last one. Now you recognize that last one is what we call the 3 by 3 identity matrix, right? Zeros everywhere and ones on the diagonal. So this one's probably going to be a little special here. 1, and then if I cross out those two, I get 1, 0, 0, 1, minus, erase that for a second, it's going to be 0 is the next thing, and then that's 0, 0, 0, 1, plus 0 is the last thing, which is nice, and then 0, 0, 0, 1, 0. So if I do the determinant here, this would be 1 minus 0, or just 1 times 1. Oh, minus 0 plus 0, just 1. Easy speasy, right? I didn't even have to bother doing the determinants. So yes, so this is a little bit what we're doing today, reviewing multiplying matrices, finding the inverse of a 2 by 2, using that inverse to solve a 2 by 2 system, kind of the main thing, and then this process of finding the determinant of a 3 by 3.